So we turn now to another theorem that is important to finding extrema, and this theorem is sometimes referred to as Fermat's theorem after the person who first proposed it. There was about 400 years ago, there was a French judge, actually, a judge and lawyer in France, whose hobby was mathematics, and he actually came up with a lot of the mathematics that we know today. So even though he wasn't a professional mathematician, he's still considered one of the greats in mathematics. He's actually better known for a theorem called Fermat's last theorem, which I won't go into the statement of it, but it's just interesting because he was scribbling in one of his math books one day and wrote in the margin of the book, he said he proposed the proposition of the theorem and said there's a marvelous proof of this theorem, but unfortunately the margin is too small to contain it, and then he died. So the theorem came to be known as Fermat's last theorem, and all of mathematics went on a 350-year search for the proof that he had until 1993, when a mathematician named Andrew Wiles at Princeton, announced to the world that he had proved Fermat's last theorem. Anyway, that's a little bit of a story. Has nothing to do with the theorem we're about to refer to today, which is about to describe now, which is called, usually just referred to as Fermat's theorem. In any event, what it says is that if f has a local minimum or local maximum at x equals c, and c is in the interior of f's domain, then either f prime of c is 0 or f prime of c does not exist. So in other words, where a local extremum exists, what we know about the function is that either its derivative is 0 or the function is actually not differentiable at that point. As usual, the words are scarier than the actual concept, so the picture I think is very illuminating. Let's take a look at this picture. If you see what the picture shows, I've marked here 2 points where local extrema occur. It's quite clear from our definition of local mins and maxes that this is a local max, and this is, work it a little differently, this is a local min. Now, what do we see about these 2 points? First of all, at C2, it's fairly easy to see that at a corner, we know that a function is not differentiable. It doesn't have a derivative because depending on which side you approach that point from, you would conclude either that the slope was this very steep positive line or the tangent to this sort of negative sloping curve. On the other hand, at C1, what we can see is that the tangent, don't want to draw it like that, the tangent at C1 is just a horizontal line. So this is really what the theorem is saying, is that when we encounter a local min or max, one of two things has to happen. Either the function has to flatten out and then turn around and go the other way. In other words, it has to start going up, then it goes down, which means that at some point, at just one instant, it must have been, its tangent must have been flat. It must have been not going either up or down. Or else there must be a corner where the function makes an abrupt turn from going down to going up, or vice versa. And we can detect these. Actually, let me just give you the name for this. This situation the function where the function flattens out and then turns around is called a stationary point. It's stationary in the sense that even though the object is still moving from left to right, at this exact point it's not moving up or down. It's like if you throw a tennis ball up in the air, there's just an instant in time when the tennis ball is not going up, it's not going down, it's stopped right in midair for just an instant, and then it comes down again. This point is called a singular point for reasons I don't want to get into. But it has to be one of these two situations. A local min or max can only happen in one of these two situations, which is kind of a nice property because what it means is that if we're searching for the local mins and maxes, we can find them simply by looking at the derivative of the function. We just look for points where the derivative does not exist or where the derivative is 0. So I've marked these as C1 and C2, and there's a reason for that. It's because there's a special name for this type of point collectively. It's called a critical point. So the term for a value of c where either the derivative is 0 or the derivative does not exist is a critical point. Some textbooks will refer to this as a critical number, which is a term that I actually prefer, although I'll go with the Thomas textbook's language. The reason I prefer critical number is that, strictly speaking, when we talk about a critical point, we're referring just to the number. Like, for example, what I've drawn here is I've drawn a function that clearly has a local maximum at that red dot. Now, the red dot can be described as x equals 1, or it can be described by the ordered pair 1, 2. regardless of whether we use the term critical point or critical number, if I say, what is the critical point? The answer is 1. It's not 1, 2. In other words, I'm referring specifically to the x value where this point occurs, not to the entire point. There's a reason for that that will probably become more clear when you evaluate critical points in higher dimensions if you go on to calculus 3 at some point. But for now, just understand this is the terminology. When I refer to critical point and critical number, refer to the same thing. And when we refer to either of them, what we're talking about is the x value. In other words, the value from the domain, not the pair of values that gives you the point. So there's one more thing that we need to know before we can get to the main process that we're going to learn in this section. And that is the fact that for a function defined on a closed and bounded interval, AB, the absolute extrema always occur at one of two types of places, either the critical points or the endpoints. Now, we're actually not, since we haven't put in here the condition that the function is continuous, we're not even guaranteeing that it has absolute extrema. But if it does, they can only occur at one of two types of places, at critical points and at endpoints. So with that, we'll get to the process of finding the extreme values, the absolute extreme values of a function on a closed and bounded interval. That process is called optimization. So this is the central process that we learn in this section of the book, putting together all the different things from the previous parts of the video. This is how to find the absolute minimum and absolute maximum of a continuous function on a closed and bounded interval. The process, which flows from what we've been talking about, is as follows. First, you find the derivative of the function. Next, you find all numbers c where either f prime of c is 0 or f prime of c does not exist. Those are the points where the function either flattens out or where something like a point happens. These are what we call the critical points. Next thing we do is evaluate the function, not the derivative, but the original function, at all critical points and at the endpoints of the interval. The reason we do this is that the only places where absolute extrema can exist are at the endpoints or the critical points. So those are the only ones where we actually need to look at the values of the function. And once we've evaluated f at the critical points and at the endpoints, the highest value that you found in step 3 is the absolute maximum, and the lowest value is the absolute minimum. That's the process.